All right, so transient absorption spectroscopy. So again, like Hanwei said, I'm molecular photochemistry, photophysics. I care a lot about shining light on molecules and seeing what happens to them. And it turns out a lot of different things can happen, right? You can have emission up here, phosphorescence, fluorescence. You can have internal conversion, electron transfer, proton transfer, excimer formation, photochemical transformations, a whole bunch of different stuff. And I realize you guys are not chemists or physicists, probably care more about solid state materials, but most of this still holds true for materials chemistry related things. And so once you pump energy into a system, it's in an excited state. That energy has to go somewhere. It can go to making breaking bonds. It can give off energy. It can do vibrations, all sorts of different stuff. And so whether it's molecules or materials, the same general principles apply. And so not only can a lot of stuff happen, but it can happen over very different time scales. And so here's just a graph showing from femtoseconds to a second time scale. And so this is 15 orders of magnitude across temporal windows. And so just going back to some of those events, excitation is basically instantaneous. That's where you pump energy into a system and it moves an electron up to an excited energy level, or it generates an excited state. You can have things like structural changes like isomerizations. Those can occur in the 100 femtoseconds to picosecond timescales. You can have things like internal conversion, which is vibrational relaxation down to a level. You can have fluorescence, which is emission from singlets, intersystem crossing, which is going from singlets to triplets, phosphorescence. You could add a whole lot of things to this list. You could add photochemical transformations, decompositions happen on this entire timescale. And so, like I said, there's a lot of events, and these events happen at very different times. And so, again, photochemistry falls under basically the entire window. And so when looking at these changes that can happen after something absorbs light, there's some different ways that you can probe these behaviors. And so the first one, exciting the molecule or material, that's absorption spectroscopy, just how many photons get absorbed by the system. If you want to do like a photochemical transformation and want to see what it changes into, you're essentially taking a snapshot before and after light happens. And so you can do things like NMR, mass spec, X-ray to see compositional changes. And you could do XPS, SEM, TEM, just seeing how it changes after you shine light on it. There's other events like phosphorescence and fluorescence where a photon is given off. So it absorbs a photon, typically goes to lower energy, and then gives off that photon, or gives off an additional photon. And so you can use steady state and time resolved emission to see those. But everything else on this list, they're non-radiative decay processes. And so by non-radiative, we mean they don't give off photons. And so you can't monitor them through the light they generate. These are what we'd call dark processes, right? And so change is happening, but as far as you can tell looking at it, it's not so obvious, right? And so after that light is absorbed, all these are dark transformations and all could be occurring simultaneously. So you have to figure out some way to resolve those events. And so an example of this that you might not care about directly, but it turns out you care about a lot, is this particular process here. This is rhodopsin. And so this is actually how vision in your eye works. And so rhodopsin is one of the photochemical sensing molecules in your eye. And so it basically starts out as a particular structure. When light shines on it, it does a trans to cis isomerization, giving you something like this. And then it undergoes a whole bunch of different transformations before it goes back to its starting point. And then you can catch a photon and see something again. This is literally the foundation of your vision. And so what's key to this is there are a lot of steps in this process. The first one happens in 200 femtoseconds, then picoseconds, nanoseconds, microseconds, milliseconds, minutes, again, spanning several decades of time. Not only that, but you have structural changes along the way. And here's one example, turning into this guy, eventually going back over here and recombining with retinol. And so each one of these steps not only happens at different time scales, but also you can see a wavelength under each of these. And so it basically tells you the color of each one of these species is different. And so if you really want to understand how the human eye works, you need to resolve this both temporally and spectrally. And so you need to see what color changes are happening and what time intervals they happen at. And so light initiates the process, but there's a whole bunch of steps that happen afterwards. And so that's when we turn to spectroscopy. And so you guys just got done with electrochemical measurements. You're moving on to spectroscopy. The primer that most people are familiar with is simply absorption spectroscopy. And so that's the starting point for most spectroscopic measurements. It's simply passing light through a sample, how much light actually goes through. And so if you took undergrad general chemistry, you probably did this experiment. It's basically do a measurement without the sample, put the sample in, do the measurement, see how much light is absorbed. An iteration on that, if you want to measure the photons coming off, you do something called fluorimetry or phosphometry if it's a long time scale event. And so what you effectively have is some light source. You're hitting your sample with light. That sample is going to absorb that light, give off those photons, and you'll detect it at some kind of detector. And so in both cases, you have a source and a detector. It just depends on what you want to measure. But today I'm going to talk to you about transient absorption. So it kind of takes aspects of both these measurements and combines them together, giving you a transient or time-resolved measurement. And so basically you have, for the slower timescale measurements, you have two different light sources and then one detector. And so your two different light sources, one acts as a pump to excite your sample, the other one acts as a probe to measure what the color change is over time. And I'll get into this in more detail in a little bit. And so when you think about conceptually what transient absorption spectroscopy is, if you've ever seen photochromic sunglasses that essentially change color when you bring them outside, you have done a transient absorption experiment. Not necessarily rigorously and mathematically, but you have seen this type of process happen. And so the idea of transient absorption is you have excitation, you wait some time, and then you measure the color change over time. And so when you think about this particular measurement, your excitation source is the sun. It changes the color of these glasses. When you go back inside, they go from dark color to transparent again. You can actually visually watch that transparency increase. And so you have your room lighting, you have your eyeball acting as the detector, you have two different sources. That is a transient absorption measurement. And so you have a light source, you turn that light source off by going inside, and then you watch the color change over time. And so again, that's exactly what transient absorption is. You're just doing it on a much faster and much more accurate time scale. And so you use some kind of excitation source, which is typically a laser, and then you use some kind of UV vis type accessory to see how the absorption changes over time. All right, so the reason we do this transient absorption type measurement is the human eye is not particularly good at temporally resolving events. It is on a certain time scale, but basically human vision in the brain has a temporal resolution. Basically, how fast can you see things happen? And so the answer is our refresh rate is about 10 hertz. That's our refresh rate of our brain as well as our optical receptors. And so what we can do is process 10 to 12 separate images per second. And that's why the TV, even though it's snapshots of photos, it still looks like a continuous image because our brain isn't particularly good at resolving very, very fast things. And so when you think about what that 10 hertz resolution means, it means if I shine a pulse of green light at you and then I wait 100 milliseconds and give you a pulse of red light, what you're going to effectively see is green and then red. But if I do that slightly faster, if I do this, say, in 10 milliseconds instead of 100 milliseconds, if I do green and then red, your brain cannot separate those two colors. They're too closely related temporally that you can't resolve the difference between the two. And so here you'll see yellow, here you'll see green, followed by red. And it's because of the resolution of the human eye. And so to put this in context in terms of how fast we can see things, we can't resolve the wings of a hummingbird, right? They flap just way too fast for us to see. Turns out it's about 70 hertz or 14 milliseconds per flap. Again, our resolution is about 100 milliseconds. Even trying to resolve a photo finish of a race, we can't see it. If they're within, a millisecond time, we can't see it. If they're within 100 milliseconds, we can't resolve that. And so that's why we rely on things like photo finishes. The spectroscopy of photo finishes is really cool. This isn't just a camera shot. Basically, they have a camera slit at the finish line. And so here's the finish line, and they take photos over and over again, and they spread them out on the x-axis here. So these are compiling a strip of photos, which is why you can see distortion here and here. So kind of cool spectroscopy example. But one important one, at least historically, is trying to resolve horses and horses galloping. And so many of you might have seen this before. This is called the horse in motion. This is Edward Muybridge, 1872. He did this basically snapshots of a horse running. And so it turns out this was a pretty important event in terms of spectroscopy, at least visual spectroscopy, and in terms of trying to resolve things. And it turns out this was the byproduct of a bet. It depends if you believe the story story or not, but basically Leland Stanford, who donated money to Stanford University, super rich guy, he had oil companies, all sorts of things. He also had a horse racing track. And when rich people were sitting around, they decided to have bets on things like, does a horse's hooves, do they all leave the ground at the same time? And so the human eye can't resolve that. It's way too fast for us to actually see. So what Stanford did is he paid Edward to actually figure out whether a horse's hooves leave the ground, which is kind of crazy, but he did. And so here's what Muybridge did. He basically set up a whole bunch of cameras. He had a backstop over here. He had a bunch of string across. When the horse ran across those strings, it took a snapshot. And so he's taking photographs over time as the horse breaks those strings. And so you stitch all those images together and you get something that looks like this. And so apparently Stanford won the bet because you can see all 4 horse hooves are off the ground at one time. And so not a chemistry or science application, but it is a biology, a biomechanics type study, and one of the first of its kind to actually break down the horse gallop. And so with his particular instrument, he could resolve things on a scale of 0.001 seconds, and that was in 1877. And so basically this measurement had a 1 millisecond time resolution, which again, not bad for 1877 and early photography. Needless to say, we've gotten a whole lot better at spectroscopy over time. This is a graphic that came out with the Nobel Prize in Femtosecond Spectroscopy, basically looking at progression of human timescales and evolution of how we measure those timescales. And so humans can perceive things on, everything from decades to milliseconds. You have things like stop flow, flash photolysis in the 1950s, lasers are introduced in the 1960s, picosecond chemistry, and then femtosecond chemistry. And so what's crazy about this is in terms of our human progress, we have gotten 17 orders of magnitude better at measuring time, which is absolutely astounding. When you think of the quality of measurement of anything, I mean, the only thing comparable might be like, I don't know, magnetism or conductivity or something like that. But temporal resolution, we've gotten so much better over even a short period of 150 years. And so just to give you context, what 17 orders of magnitude is, that's basically the size of bacteria versus size of the entire solar system. So that is a non-trivial amount of change over a given time. And so here's the same data basically shown in graphical form. Here's year versus time resolution and how we've gotten better and better. Major breakthroughs, laser was a key one in terms of spectroscopy, in terms of being able to measure things really fast. Before that, we had to use like flash lamps and light bulbs, like those old flashes you'd seen on cameras. When the laser was introduced, that basically changed everything. And so that was the stepping stone towards transient absorption spectroscopy. And so remember, this technique is all about monitoring change over time. And in this case, you're monitoring color change. And so here's the basic setup again. You essentially have a source that excites the sample, and then you have some source that lets you measure the absorbance of the sample over time. And so the reason you want to do this, at least from a molecular standpoint, even a material standpoint, is every species that we change something into has a different color, or it's going to have some change in color associated with it. And so if we have some kind of acceptor and a chromophore molecule, if we shine light on it, we can generate an excited state. Here's the acceptor, here's the chromophore star. The star just indicates that it's an excited state. An electron is bumped up to a higher energy level, and we can have that electron transfer to this different species. And so in this case, it's A- because it's reduced, it's gained an electron. We're going to have chromophore plus. And so you can generate these electrochemically, but you can also generate those with flashes of light. And so one of the key things is we have A and C, we have A and C star, we have A- and C+. Each one of these is going to be a different color. And so the C in this case might look like this. When you make C star, it might look something like this. When you make C+, it might look something like this. And so each one of these is going to have a different color associated with it. And so if we can monitor color over time, we can figure out how fast these rates of various processes are. And so the way we do that again is through transient absorption. And so we basically have a ground state absorption spectra. We're going to excite the sample with a pump is what we call it. And then we're going to measure the absorption spectra again, which is known as a probe. And so essentially what you're doing is your first excitation is pumping your ground state into some kind of excited state manifold. In this case, we call it S1. And then from there, it can relax down. But before it does, it can still absorb more photons. And so that's what an excited state absorption is the photons that are absorbed here. And so the thing about absorption, and we call it transient absorption, and we call it UV-Vis an absorption measurement, we rarely actually measure absorbance. So that's not actually what we're measuring. What we actually measure is transmittance through the sample, because we can only detect signal. We can't really detect a loss of signal. And so for an absorption measurement, if you did this in Gen Chem, the idea is you have some light going on the sample, and you have some light going out of that sample to the detector. And so keep in mind, there can be scatter, there can be absorption, there can be reflection, there can be all sorts of stuff. And so for a transmittance measurement, we just do a ratio of these two, right? It's power out over power incident, or P naught. And so in this case, it's a percentage of the light that actually got through the sample. So if it's 10% transmittance, only 10% of the light went through. For convenience, we convert this transmittance number to an absorbance number. And we do that so we can put the percent onto a logarithmic scale. And so the negative log of transmittance is absorbance of the sample. And so we measure transmittance, which is how much light goes through, but we convert it to absorbance because absorbance is a convenient unit to use when describing materials and molecules. And so here's the scale, the proportionality. Again, absorbance is a logarithmic scale, transmittance is a linear scale. And so you can see if you have an absorbance of 1, it means you're transmitting only 10% of the light. If you have an absorbance of 2, you're transmitting 1% of the light. And so both are related. They both mean similar things. They're just represented on different scales. And so again, what we actually measure is transmittance. What we report is typically absorbance. And so here's how the TA measurement itself works. And so I just showed you the math behind doing an absorbance measurement. This is just going to be doing an absorbance measurement over time. And so here's stepwise how it happens. You take an absorption spectra of your sample, that is, you measure here, and then you do a flash of light from the secondary source, and then you do another absorption spectra of the sample. And so it allows you to see the color before and after you shine that extra light source on it. And so here's what it looks like temporally. Take some kind of absorption spectra, see what color the sample is. Then you have a pump, which puts it into an excited state. It makes it energetically excited, and whatever processes are going to happen. And then over time, you probe. You do another absorption spectra, another absorption spectra, another absorption spectra. And you're essentially watching, based on the time interval between them, how the transformations occur over time. And so this is watching color change over time. And so all of these are the excited state processes. This is the ground state spectrum. And so this is how we resolve that. You know, if an event happens in 200 femtoseconds, you wait 200 femtoseconds to actually measure that absorption. Wait longer to measure the next step. Wait longer to measure the next step. And so one thing that we have to worry about with transient absorption, unlike ground state absorption where you just do an absorption measurement, with transient absorption, we have to do something called a difference spectra. And this is just based on statistics of likelihood of exciting materials. And so let's take a material here. We'll call these green molecules or green particles or quantum dots or whatever you want. These are all in the ground state. And so when I shine light on them, they're going to transform into the excited state. And so we'll represent the excited state by this yellow sphere. And so green spheres are going to turn to yellow spheres after they absorb a photon. The hard part is, even with a really intense light source, you don't excite every single molecule or particle. Instead, you just excite a fraction of these guys. And so even under laser conditions, you might only excite 4 of those particles or molecules. And so that gives us a problem, right? Because here's the absorption spectra dominated by the green. Here's the absorption spectra after the pulse, still dominated by the green, right? And so there's going to be a slight change in spectra between these two, but it's not really discernible because the problem is you're only changing 4 of the molecules. And so it's not going to be obvious what this color change is. And so again, you're going to have a certain number of molecules in the ground state, and you're going to have some in the ground state with a few that are going to be in the excited state. And so we can't just use the spectra as a raw interpretation. And so what we do instead is we do a difference spectrum. And so what we have is basically an absorption spectra without the pulse, that's before the light, and then we have an absorption spectra after the pulse, and we're going to subtract the two to give us a difference spectra, or a delta A. And so here's the absorption spectra before the pulse, here's the absorption spectra at a given time after the pulse. If we subtract the two, we get something that looks like this. And so while these two are not readily discernible, all of a sudden if we have this, we can see features. And notice the numbers are really small. These are like milli OD, where these are in, 1 OD. And so the signal is very small, but it's enough to discern a difference between the two. And so this is what a difference spectra looks like. And so if you look at the math, it basically says if it's negative going, you lost something. If it's positive going, you've created something new. And so this, whether it's negative or positive, it tells you something went away, something appeared, and it depends on the sign of it. And so I'll just clarify what that means. So here again, you're just subtracting the two of those guys. You have a certain number in each state, and this is the difference spectra associated with those. And so what this basically means is in a difference spectrum, you see positive going peaks and you see negative going peaks. And so what you've done with your pump is excite your system to a higher energy excited state. And once in this state, it no longer has this transition, right? Because you've depleted some of those ground state species. It can't go up to this excited state again. And so the intensity of this transition decreases. And that's where you get this negative going peak. It basically says some of those in the ground state don't exist anymore. So the signal intensity for that absorption decreases. It can't happen. You also have another transition where you can go from this excited state to another excited state. And so that's called excited state absorption. And so that's a positive going peak. This transition didn't exist when everything was down here, but now that some molecules are here, then this transition can exist. And so you have a positive excited state absorption feature. One thing to note on these, you don't typically see it because there's ways to correct for it, but essentially you can excite to this S1 state, and then your probe beam actually lasers the sample, so you can get stimulated emission out of the sample. And so that looks like a negative going peak because new photons are being generated and hitting the detector. It basically looks like more light is transmitted, but it's not. It's more emission that's hitting the detector. And so you correct for this by doing the transient absorption without the probe beam, but that's a little too nuanced. But anyway, take home here is if something goes away, you have a negative going peak. If something appears, you have a positive going peak. And then if you can track these peaks in these peak positions, you know what species are being formed, you know what species are going away. And so you can actually track over time what happens. All right, so we don't measure absorbance. Again, we measure transmittance, and so we have to do a little bit of math to make this happen. This is just formalizing. I said delta absorbance. Really, it's just the delta, negative log of transmittance. So at the sample, we measure power in and power out. So there's basically the translation. And so our math, it turns out, simplifies quite a bit because at time zero, we essentially have this equation right here. We have some incident power on the sample, and here's the power that actually goes through the sample. At time t, the incident power still stays the same. The power that goes through the sample is going to be different. And so of these two equations here, the log aspects of them, this is the same as this. This guy is different from this guy. And so basically we can do a little bit of algebra, plug this into this equation here, and then we get this. So our delta A, our change in absorbance, is simply the log of power at zero. This is the transmitted power before a laser pulse. And then power at time t, that's after that pump to excite the sample. And so if we know the intensity that goes through the sample before the laser pulse and the intensity that goes through after the laser pulse, we can calculate the delta A. So we don't actually have to deal with absorbance spectra before, absorbance spectra after. All we need to know is how much light is transmitted before the pulse and how much is transmitted after the pulse. All right, so going back to this, with all that in mind, I've talked about this a few times, but essentially we have a measure absorbance, do a pump, and then measure absorbance again. Essentially all we need to measure is the P at time zero, which is the light that gets through here. Then we pump the sample, and then we measure the light that goes through at time t. And so if we know those two, all of a sudden we know the delta A of the sample, we know what the difference spectra is. And so If you're doing a single wavelength measurement, what you end up getting is something that looks like this. You basically have nothing, nothing, nothing. You have baseline because P0 equals P at time t, and then you have a laser pulse that excites the sample. You get a spectral change, you get a transmittance difference, you get an absorbance difference, a color change of the sample, and all of a sudden you get a positive delta absorbance. This basically tells you something new is generated, and then that something goes away over time. And so this is what a single wavelength transient absorption trace looks like. It's basically delta absorbance over time, and this time change tells you how fast those events occur. And so that's how you can resolve a rate. You can fit this with an exponential or bi-exponential or stretched exponential and actually put a number to how fast that sample changes into something else. You can do this single wavelength, you can do this full spectra. It depends on what your setup is. You guys are physicists, so you understand playing with instrumentation and turning knobs and putting in different detectors. So you can do full spectrum detection. And so here we'd have a pump, we'd have a probe, we'd have some kind of prism spread out over a detector. You can actually measure all wavelengths simultaneously. And so just like a standard UV vis that uses a diode array or a CCD or some area detector, you can do the same thing with transient absorption. And so you can see it's basically acquiring all wavelengths simultaneously. Here's something that went away and over time it's going back. Here's some new species that was formed and over time that new species is disappearing. Or you can do single wavelengths. So take your monochromator, pick one particular wavelength, just measure that. Typically you'd use some kind of PMT detector, and then you'd see something like this. And so these two graphs are representing a similar phenomena. It's just this looks at one wavelength, this one looks at all wavelength with different time slices. And so this is the one that you'd typically use to fit the data and get numbers out of it. This is the one that you would typically use to see what peaks are forming, what peaks are disappearing, trying to define what species are going on. And so the two are related. You can actually convert one into the other. You can take a bunch of single wavelengths and essentially generate a full spectrum data. They're translatable between the two. In fact, our Femtosecond TA at FSU has really nice software where you can do time slices of this to give you this, or you can put these together to get this. It's all measuring the same thing. It's just measuring it in slightly different ways. All right, so like I said, we're measuring these events over long periods of time, right? We're looking at color change. We're seeing how the color changes with pulses of light. And so we have a pretty big time interval that we have to measure that. And so you can't measure all these different time ranges with the same instrument, right? Like we couldn't use Edward Muybridge's setup to measure molecular reactions. It's very different time scales. And so what we effectively have are several different instrument time scales that we deal with. And so one is Nanosecond TA. You can also get Picosecond TA, you can get Femtosecond TA, and there's people building Attosecond TAs. And it's one of those things, you cannot use a Femtosecond TA to measure 1 second time intervals because it's just too slow that the instrument can't see it. And so there are tricks we have to play in terms of instrumentation to actually measure all these different time scales. And so I'm just going to briefly walk through the progression, how we've gotten better and better at measuring things temporally. And so Milli to microsecond TA is perhaps conceptually the easiest. In fact, this is the earliest example of transient absorption. This was first developed in the 1950s. This is Eigen, Norsch, and Porter. Here was the reaction they studied. And so not a particularly sexy reaction, but it's very interesting in terms of the fundamentals they were able to get from this. And so what they did is they took hydrogen iodide in the gas phase, shined light on it, got H and I. They took chlorine, shine light on it, get chlorine and chlorine. And so this is a homolysis reaction or a photolysis reaction where you cleave the bond between those two species. And so here's how they did it. They basically had a tungsten lamp, which is just a standard tungsten light bulb, had some kind of filter. Here's their sample. Here they had a monochromator and they had a photodetector. And so they had an oscilloscope to basically read that output over time. As the light hits the photodetector, the voltage increases, and then over time it decreases. They read that out at the oscilloscope. And so what they did for their pump source, keep in mind, 1950s, they didn't have readily available lasers yet, right? And so what they essentially did is use a photography lamp, like one of those flash bulbs that you would have on an old school camera. They took that, a 1 meter quartz tube, they put it across the sample here, and they essentially pulled the switch. And when they pulled the switch, they got a flash of light, and then they just monitored the color change in this species over time. And they got something that looked like this. And so not particularly particularly high resolution. You can see baseline. There's the flash of light. You can see they can monitor the event over millisecond timescales. Again, this isn't particularly fast, but this was the fastest any human had resolved a chemical reaction. And so that's why in 1967 they were awarded the Nobel Prize for it. And so this spectra right here was worth a Nobel Prize. In all honesty, it probably didn't really matter what they measured, just that they were able to measure it fast and show that the concept is viable. And so again, 1967 Nobel Prize in Chemistry. The description for it was for studies for extremely fast chemical reactions affected by disturbing the equilibrium by means of very short impulses of energy. I highlight extremely fast and very short because, as we know, this is not the fastest we've been able to do. We've moved on since this 1950s type research. All right, so a major breakthrough for us, at least in terms of time resolution, was the introduction of the lasers in the 1960s. And so we no longer had to worry about a camera flash, which is relatively slow. Anytime you have to worry about thermal emission and things like that, you have heating, you have cooling cycles, it's relatively slow. But when you have a laser that has a Q switch and can discharge very quickly, you're basically narrowing the pulse. And so one of the fundamental limitations of transient absorption is how short can your pulse of light be? And so if it's a light bulb, if you're turning a light switch, it's slow. If you're using a flash lamp, it's faster but still slow. If you can do a laser pulse, you have narrowed down the width of your pulse, which means you can measure things more and more quickly. And so again, the introduction of the laser, especially neodymium YAG lasers and argon ion and nitrogen lasers as well. Basically, you have a laser pulse. You can have a pulse generator that communicates between your detector and your light source. And then you can have just a steady state xenon lamp or a flash lamp. And you basically laser pulse, measure the absorption over time. You can get this down to the nanosecond type regime. It depends on your pulse width, which on a standard neodymium YAG is about 5 nanoseconds. And so this gets us from the millisecond, microsecond regime that Porter and Norsch were looking at down to a nanosecond type measurement. And so turns out now these instruments are commercially available. You can literally go out and buy a nanosecond transient absorption spectrometer. Basically, you couple any of these spectrometers to a neodymium YAG laser, pulse it, have them couple the timing, and you can have a nanosecond transient absorption setup. Thankfully, at FSU, we do have one of these systems. So over at in CSL 3701, we have the Edinburgh LP980. So you can see the setup here. Basically, there's the laser. This is a continuum sure light laser source. That's a neodymium YAG, about 5 nanosecond pulse. Here's an OPA, which allows you to tune the excitation. And then here's the spectrometer. And so basically on this side over here, you have a light source. Over here, you have a detector. You're shooting the laser in, hits the sample. Then you probe by going the light source through the sample. And so this is pretty much the scheme that I just showed you guys. In this case, they can detect between 280 and 1500 nanometers, or they can excite between 280 and 1500 nanometers and detect 300 to 1700 nanometers. So basically the whole visible plus the near infrared region. And so yeah, if you want to watch any color change that's happening on the 5 nanosecond to 1 second time scale, this is an instrument that can do it. You can watch those color changes, especially in the visible and near IR regions. If you want to go faster than a nanosecond, there's some games that you have to play. This isn't as popular, but basically what you can do is you can have a laser, mode-locked laser that gives you a little bit more temporal resolution, and you can use something called a streak camera. I wish I could go into the details of a streak camera because it's such a cool technique. But basically the idea behind a streak camera is you have an area detector, and you can actually apply a voltage and move the electron beam over time. And so you can basically resolve time with spatial control over the signal. And so really cool technique. Look up streak cameras. They're awesome in terms of resolving time. This can get you down to about the picosecond time range. And so you can jump from nanoseconds with a standard flash lamp and a standard PMT detector. You can go to picoseconds with a flash lamp and then a streak camera of some kind and a mode-locked laser. But if you want to go sub-picosecond, things start to get really hard. And I need you guys to understand how short a picosecond is. We're talking in 10 to the minus 12 seconds. That is super, super fast. Like when your picosecond time range, like the length of your cord matters because your electrical signal starts to compete with your temporal resolution. And so you really need to start worrying about how things communicate and how fast they communicate. And so if you want to measure sub-picoseconds, you got to get really, really clever. In fact, you cannot no longer, on this time scale, you can no longer use two different sources and time them up because they can't communicate fast enough and resolve it fast enough. And so you got to get really, really clever, which is why in the 1980s, Zoel introduced femtosecond spectroscopy. He got the 1999 Nobel Prize in Chemistry for the way that they did it. You'll notice they didn't say very fast anymore. Instead, they said, for his studies on the transition state of chemical reactions using femtosecond spectroscopy. And so this is 6 orders of magnitude faster than what the 1967 Nobel Prize was, and this is for femtosecond spectroscopy. But the major breakthrough that allowed us to start getting faster and faster is how we do our pump and probe. And so you'll notice this has very similar components. You have a laser here. You're going to have a detector. Well, you'll have several detectors depending on how you want to do it. Your sample is right here. Here's the measurement of the actual absorption change. But something that this technique does different that they didn't do previously is basically you're only going to use one light source. And so the reason you're going to do that is because you're going to control the pump and probe from one light source. And so what basically happens is this laser generates a pulse of light. And so here we're going to have a beam splitter. And what that beam splitter is going to do, it's going to split that initial pulse into 2 separate pulses. And so one of those pulses is going to go through and be the pump. That's going to go through and hit our sample and excite our sample. We're going to have a second pulse of light that goes through, and it's going to go through something called the delay stage. And after it goes through the delay stage, it's going to eventually get to our sample. And so what's really cool about this time scale is you can control the time difference between when the pump arrives, which is going directly, and when the probe arrives, depending on how long that light travels. And so light travels about 1 foot in a nanosecond, right? And so if you change the path length by a foot, you've changed the time by 1 nanosecond. And so by changing the distance this travels, let's say you cut it off here, it goes faster, cut it off here faster, cut it off here, it goes longer. And so this delay stage, essentially changing the distance of this mirror, controls how fast your probe gets to the sample. And so, yeah, crazy innovation, but in this case, you're controlling the time between the pump and the probe based on how long the beam of light has to travel. And so I'll break this down in terms of the actual measurement here. And so if you're going to do femtosecond spectroscopy, basically what you have is a very short pulse of light. It's typically on the 100 femtosecond type time scale. And then your molecule is going to be excited, and those molecules are going to decay. Or your sample is going to be excited, and that sample is going to decay. But we can't monitor this with a simple detector because we can't communicate between the source and the detector anymore. We need to use 2 light sources to measure this. And so here's the way you do it. You basically do your blank absorption, just pass your laser through it, and then you're going to do a pump pulse. And so you're going to have pumps going to go through the sample, and then you're going to have a probe. And so this delay between your pump and your probe has to do with the distance that it traveled. And so going back to this diagram, you have your pump going through directly. It's not delayed at all. It's going to hit here immediately or quickly. And then you're going to have some delay associated with how long this path is. And so by changing this path length, you're changing how quick the next pulse is. And so what you can essentially do then is you're measuring the light that's going through the sample before the pump, and you're measuring the light that goes through after the pump. And so here you can calculate the transmitted light at T1. And so you can do the same thing again by changing the path length. So if you make that path length longer, you're going to delay the time between the pump and the probe, and you're going to have some temporal difference between these two. And so you're going to get light transmitted at a given time interval after that. And so pump was the light that goes directly. Probe is the light that has to go through a longer path. By making that path even longer, then you have a longer delay and you can probe later in the sample. And so essentially you measure transmitted light once here, and then you'll measure transmitted light here, and then you'll do that over and over again. And so by graphing or by accumulating that data at different distances of light travel, you're accumulating data at different time intervals. And so you can take this transmitted light, change it to delta absorbance calculation, and you get a graph that looks like this. So at this time interval, the intensity was high, then it goes down, then it goes down, then it goes down. All of a sudden, we've stitched together what looks like an exponential decay from individual snapshots based on the secondary probe. And so again, just to reiterate, you have a pump that hits the sample directly. You have a probe that's delayed depending on how long the distance it has to travel. If you make that distance longer, you can make the probe later. And then you take that piecewise, construct something that looks like this, and you can actually watch the delta absorbance decay over time. And so, yeah, basically this just shows the math behind if you have a new species growing in, your transmitted light decreases, which means your delta absorbance is a positive value. If you have increased transmission of light, where the light was here and then after the pulse it's here, all of a sudden you have more transmission of light, which means a negative going signal. And so just like we saw before, if something goes away, it's a negative going signal. If something grows in, it's a positive going signal. So you can get delta absorbance from a piecewise measurement. And so, yeah, that's kind of what the instrument looks like. At least this is one variation of that instrument. Again, the key to this measurement is this delay stage right here. It's basically a super high resolution mechanical device that basically changes where this mirror is positioned. So if the mirror is positioned here, it's fast. If the mirror is positioned here, it's slow. And so what you do is you incrementally move that mirror and you do measurements. And if you know the distance this mirror moved, you effectively know the time between when that excitation beam, which is the blue one here, hits the sample, and then when the probe hits the sample. And so again, you're controlling temporal resolution based on how far that mirror is moved on a delay stage, which is kind of, again, that blows my mind every time I think about it. It's using geometric space to control temporal resolution, which is what you have to do when you get to femtosecond timescales. All right, so femtosecond, up until fairly recently, we'll say the last 10 years, femtosecond was one of those techniques that was relegated to a expert's lab, like people that exclusively do femtosecond spectroscopy. They build the instruments from scratch, they calibrate it, so on and so forth. You get the really, I want to say messy laser tables, but very optomechanic rich type laser tables, and you use a whole lot of mirrors to direct it and time it and all sorts of things. More recently, commercially available systems have become available. So you can buy femtosecond lasers, you can buy femtosecond spectrometers. What's really nice is some versions of these actually have a motorized mirror, so it does things like auto align. So rather than using a business card and trying to align things manually, you can actually use motorized mirrors and have automated type alignment processes. And so as of last year, again at FSU, we have a commercially available femtosecond TA system. And so this is the coherent Estrella laser. It has an OPA associated with it. Here's the delay stage, and here's the spectrometer that actually measures things. And so if you want to check this out, it's in CSL 3701. This gives us resolution between about 250 femtoseconds and 8 nanoseconds. And so there you can see the excitation and detection. This is a CMOS detector, so it can detect the full spectrum at a time. And so really cool that people are already publishing papers on this. So if you're interested in ultra-fast transient absorption measurements, this is the go-to instrument at FSU. A side note, there's an open space here. This was actually really intentional. We just recently got a grant to get a ultra-fast emission technique, which I could give you guys an entire talk about how you measure emission on femtosecond timescales, but we have an ultra-fast emission spectrometer that'll be inserted right here. So uses similar concepts, but uses up conversion to measure it, but we won't get into those details. There's a push recently to move down even faster than femtosecond spectroscopy. So here's the graph talking about the laser introduction in the 1960s. You can see the sharp decline in time. Notice that this is, again, 10 to the minus 10 going 10 to the minus 15. That's femtosecond. Here's a more recent zoom in on this graph. You can actually see this portion right here, this little S-curve here. That's where we got 6 femtosecond pulses. All of a sudden in 2000, people started doing attosecond pulses. And so basically making shorter and shorter pulses of light. If you guys want to read more about this, Nature Physics 2007 had a really good article describing how you get attosecond type pulses. In all honesty, I don't fully understand it. It has to do like with elastic recoil of electrons within a potential energy well, but basically you're just trying to make shorter and shorter pulses of light and then doing very similar to the transient absorption we just saw. And so, yeah, when you're talking about attosecond, you're no longer watching like chemical transformations or vibrations or anything like that. It's way faster than that. And so you're actually watching the electrons as they're promoted. You're watching electrons as they're ejected. You're watching them as they change between states. Like you're watching the moments of excitation. And so there's only a few people on planet Earth that can do these types of measurements. But yeah, you're watching immediate transformations that occur, which is kind of crazy. So yeah, tunneling spectroscopy and streaking spectroscopy and Auger decay and all sorts of really, really fast events can be resolved with attosecond. And so, yeah, that's the temporal resolution over time. We've kind of taken this journey together, starting with Edward Muybridge and going all the way up to attosecond spectroscopy. I think where the current record stands is something like 67 attosecond pulses of laser light. This might have been broken recently. I honestly haven't kept on it. But yeah, if you want to go below femtoseconds, we as humans can do that, but only a handful of people on Earth can get something this fast. All right, so we talked about a whole bunch of different events that can happen on a whole bunch of different time scales. We talked about all the different instrumentation that you can use to resolve it using this transient absorption type technique, which is basically a pulse of light, and then you're watching color change over time. And so if you want to watch emission, sure, time resolved steady state emission. If you want to see transformations, you can do that NMR mass spec X-ray. If you want to watch these dark events, transient absorption is the go-to tool to do it. You're doing a pulse of light and watching the color change over time, and each one of these different processes gives you a different color change. And so one of the really hard parts about transient absorption is it's easy to get a spectrum. It's hard to assign which one of these guys it is. And so if you have something like electron transfer, what you're going to want to do is use some kind of electrochemical technique to artificially generate what you think the species is. And so if you steal an electron from a material and get a color, you should get that same thing by transient absorption if you think electron loss is the mechanism. And so that's one of the hard parts about transient absorption. All right, that is the end of my transient absorption lecture. Do you guys have any questions?